Here we're going to talk about some important issues when we do digital processing of continuous time signals. In our previous discussion, we have assumed that the sampling frequencies is large enough and there was no aliasing. But what if the sampling frequency is not large enough? How to avoid aliasing? Alright, from the sampling theorem, we know that if the sampling frequency is given to us, omega s, and there is no aliasing, if omega c is nicely band limited is equal to 0 for all omega greater or equal to omega half omega s. What if this condition is not satisfied? There will be aliasing, right? But we don't want aliasing. So what we do is to apply an anti-aliasing filter. Suppose we are given as C to D converter with the sampling period t, and we want to sample a signal xc. This xc may not satisfy the sampling theorem, so what we do is we first apply a anti-aliasing filter. This HAA is anti-aliasing filter, and it's an ideal low-pass filter. It's band limited to with its ideal low-pass filter with a cutoff frequency omega s. All right. So with such an anti-aliasing filter, the signal here at the output of the anti-aliasing filter will be nicely band limited to omega s over 2, and there will be no aliasing. Suppose this is our xc here, and omega s is given to us, and it has some non-zero frequency component beyond omega s over 2. Okay, so we apply the anti-aliasing filter. Then xa j omega will simply be a low-pass version of xc. It will only contain the part of xc in this frequency range. Then after we sample, there will be no aliasing. Such an HAA j omega is an ideal low-pass filter, so it's actually an ideal anti-aliasing filter. An ideal anti-aliasing filter, an ideal brick wall filter. And if we observe this ideal filter, it goes from 1 to 0, sharp, straight down. There's no transition at all. Can we have such a filter in practice? We cannot, right? In practice, all practical filter has non-zero transition band, so it has to be practical. If it's a practical HAA, it would look like this. It's probably gonna straight. This is the pass band, but then it will drop gradually to the stop band, and this is omega s over 2. This is the transition band. Transition band. But one problem here is that sharp continuous time filters are more difficult to implement than sharp discrete time filter. So it's desirable to move the computation here to the discrete time. So in the continuous time, we would like to use as simple as possible a continuous time anti-aliasing filter, and then offload the computation to discrete time. One way to do this is to sample at a higher sampling frequency and then decimate in the discrete time. Suppose our XC contains some desired signal. The desired signal has cutoff frequency around omega n, and this is the desired. But it also contains some unwanted noise, and the unwanted noise are high pass noise. So this is what XC look like in the frequency domain. This is noise. Okay. And now the idea here is we use a simple anti-aliasing filter here, HAA, J omega, and when we sample T, we use T, and how is T determined? Originally, that is omega n, so omega s is 2 times omega n, right? This is the omega n is the cutoff frequency of the desired signal. But if we were to sample directly using this sampling frequency, we would get aliasing. So instead of 2 times omega n, we oversample. That means we sample at a higher frequency. We oversample by a factor of m. Okay. And the T will simply be 2 pi omega s. And now in the discrete domain, in the discrete time, let's say, not discrete domain, discrete time, we have x hat n, the output of C to D. Then we pass it through a sharp low pass. A sharp low pass with a cutoff pi over m. And then we downsample. And the output is xdn. Now let's use this example and see what we get out of this. Let me redraw xc j omega here. And let's say this is omega s, which is equal to 2 times omega n m. And we can have now we can draw HAA. HAA is this of this shape. It can have a very, very long transition. Very, very long transition. This is HAA. HAA J omega. It has a very long transition, so such a filter will be cheap to have. And at the output of HAA, we get HA. This is omega. Omega was still in continuous time. It's AJ omega. It will contain the desired signal. And also some attenuated noise, especially towards the stop end of HAA, it will be attenuated, and similarly on this side as well. Okay, this is HA, and then after this is sampled, the discrete time signal's Fourier transform x hat EJ omega will look like this. It will contain shifted copy of XA, and the next shifted copy will come here. That will be the next shifted copy. That's where the next shifted copy will be. And it will be of this shape. Okay, so after we downsample, delta n would, the omega n would becomes pi over m. Okay, so let's redraw this. This will become pi over m, and this is minus pi over m, and then it would also contain some aliased noise. There will be aliased noise because of shifted copy. And this is 2 pi. Omega s will become 2 pi. Like this. Okay, and this is unwanted aliased noise. Aliased noise. Now we can apply a sharp low-pass filter in the frequency domain to filter out this part from minus pi over m to pi over m. That's the low-pass filter with the cutoff frequency pi over m. Then what we get will be the desired signal only. It will be the desired signal only. And then after we downsample, this will be stretched to from minus pi to pi. From minus pi to pi, and this is xd ej omega. Okay, there will be stretching after after it is decimated, after x, the filtered x hat is decimated. Another important issue in sampling is the issue of quantization. What is quantization? In our previous discussion of C to D, we take samples of xct, and xn is equal to xc and t. Okay, but after sampling takes place, the samples will be stored in a computer. So how would the samples stored in the computer exactly the same as xct, xc and t? Can we store these numbers exactly in the computer? No, it won't, because the numbers stored in computers are in bits, are given in bits, so it's only an approximation. And how good the approximation is really depends on the number of bits that we use to represent each sample. And in the following of our discussion, we're going to talk about how the number of bits that we use to represent each sample will affect the accuracy of the representation. First of all, what we need is a more realistic representation of sampling. And here it is, analog to digital conversion. When we have a XCT, we first do sample and hold. To hold the values of XCT, we get X0, and then we pass it through A to D. Let's go through each block, each system one by one. Suppose this is XCT, and this is 0T, 2T, 3T. What the sample and hold does is to sample the value of XC sample these value and hold it. So here's the output X0 of a sample and hold. It would have the value here. It sampled the value of XC at multiple of T and then hold it. And then hold it. And then hold it for a period of T. So this is what the output of 0 and hold look like. It looked like a staircase. Right? And now A to D. The output of an A to D is actually binary code. The bits that's used to represent the sample. To make it simpler, let's consider only the A to D input has only a scalar x instead of a sequence, and the output is xb hat. Then this A to D can be considered as two parts. First, it's a quantizer Q. That's what we call a quantizer. And in the second part, it's a coder. And the coder output will give us the bits, xb hat. So x input, the output of quantizers is x hat, and the coder output is xb hat. For example, x is a number that is between -1 and 1, and we use 2 bits to represent x. When we have only 2 bits, there are actually 4 choices. 4 choices of representation. Suppose this is the interval from -1 to 1, the range of x, and we only have 4 choices to represent x. So one possibility is to divide it into 4 cells or 4 intervals. And this would be 0, and this would be half, and this would be -half. And within each cell, whenever x falls into this cell, it's quantized to the center value. When it falls into this cell, it's quantized to this center value, and when it's in this cell, it's quantized to this value, and it's in this cell, it's quantized to this value. And these values are quarter, and 3/4, minus 1/4, and minus 3/4. So, for example, x is equal to 0.3. Then which cell does it fall into? It would fall into 0.3, right? So slightly above 1/4, so it's right here. So it's quantized to 1/4. As another example, x is equal to minus 0.7. It will fall into this cell here, so it's quantized to this value. Okay, so this is the quantizer part. Now for the coder part, we may give each cell is represented by 2 bits, right? So we may call this a cell 0, 0, and this one 0, 1, and this is cell 1, and this is 1, 0. Okay. It was too crowded, so I have redrawn it a little bit. Now, for this x hat quarter, it will be given the code 0, 0. And then for x hat equal to minus 3/4, you will be given the code 1, 0. So, if we have an input of values 0.3, the output will be 0, 0. And if we have an input of minus 0.7, the output will be 1, 0. That's the binary code. Now let's consider the more general case. Suppose x belongs to an interval of length 2m. Okay, so here is an interval of length 2m. This is from here to here. This is 2xm from here to here. Okay, and x is quantized using b plus 1 bits. The quantizer is a b plus 1 bit quantizer in the A to D. This is a more general case than the example that we showed in the previous slide of 2-bit quantizer. Now this is a b plus 1 bit quantizer. For example, b plus 1 is equal to 3. So 3-bit quantizer, b equal to 2. Then as in previous example, we would divide the range of x into the 2 to the 3 number of cells. So we have 2 to the 3 number of cells here. And as before, in each cell, the value of x is quantized to the center. And each cell or each quantized value is given a binary code. Say this is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and then 1, 1, 1. All right? And it's in a range of 2xm. In our previous example, this is minus 1 and this is 1. Okay, that's the previous example. And the length of each interval, or the length of each cell here, the length of each cell is what we call step size, and we give it a name, step size. Step size delta will be the range 2xm divided by how many cells? The number of cells will be 2 to the b plus 1. So it's equal to xm over 2b. Now if we consider the value of x and its quantized version, it will really depend on how big the interval is or how big the step size is. What is the largest difference there is between x and its quantized version? It would be this much, right? Half the step size. That's the largest difference between x and the quantized version. And the step size really depends on xm and b. Now let's see how we can analyze the difference between x and x hat. That is called quantization error. Quantization error is defined as the difference between x hat and x. In this example here, the quantization error would be the difference between x hat and x, which will be 1/4 minus 0.3. And in this example, it would be minus 3/4 plus 0.7. And we can see that the largest quantization error would be half the step size, and the smallest would be the negative of step size. So EN is the quantization error will be between minus delta over 2 to delta over 2. For example, xn is 0.99 cosine n over 10, and we use a 8-bit quantizer to quantize xn. In this case, delta will be xm over 2 to the b. xm, suppose we use xm to be 1. And 2 to the b will be b, because a bit quantizer, so b is 7. It would be 128. And half delta will be 1 over 256. This is around 0.0064. This one is xn here, and this one is x. This one is the quantization error. And we can see that it's quite random between minus 0.004 and 0.0004. It appears to be quite uniform in this range, and that is true in general. When B is reasonably large, for example, B equal to 7, 8, or more, the quantization error can often be modeled as a random variable that is uniformly distributed from minus delta over 2 to delta over 2, and it's uncorrelated with x. When a random variable has a uniform distribution, its probability density function looks like this. 0 from minus delta over 2 to delta over 2. And the height is 1 over delta. This is the probability density function. In this case, the variance of E will be, because it has a zero mean, has a mean equal to 0, will be equal to its mean square, and it's equal to E squared 1 over delta dE from minus delta over 2 to delta over 2. And if we carry out the computation, this is equal to delta squared over 12. And remember from previous discussion, delta m is equal to 2 to the b, right? So if we plug in this relation, what we get is 1 over 12 xm squared and 2 to the minus 2b. Okay, now that we have the variance of the quantization error, now that we have the noise variance, we can compute the signal to noise ratio SNR. The SNR is 10 log 10 in dB sigma x squared over sigma e squared. We can plug in the above expression, then we get 10 log 10 sigma x squared and 1 over 12 xm squared and 2 to the 2 minus 2b. And this gives rise to 10 log 10 2 to the 2b plus 10 log 10 12 minus 10 log 10 xm squared over sigma x squared. And log 2 is 10 log 10 2 is equal to 3.01 dB. So this is equal to 6.02 B plus 10.8. 10 log 10 12 is 10.8 minus 20 log 10 sigma xm over sigma x. So what have we derived here? SNR depends on, what does it depend on? It depends on B here. The bigger B is, the higher the SNR is. But then it also depends on this ratio here. The larger this ratio, the smaller the SNR. So if we choose xm to be a lot larger than sigma x, then this will have a negative effect on SNR. So how to choose XM? In many applications, X is not uniformly distributed. The probability density function of X, PDF, spans a wide range. If we choose 2XM to match all the possible value of X, it would not be efficient quantization because the tails on two sides usually have a very small probability. The quantization in this range would not be very efficient. So typically we choose a range that contains most probability of X. When X is not in this interval, we say clipping occurs. Usually if we choose XM to be 3 times to 4 times the standard deviation of X, then the probability of clipping is a small one. For example, X is Gaussian distributed, and if we choose XM to be 4 times the standard deviation, the probability of clipping is around 0.0023, about 0.2%. Now let's plug in this 4 times X, 4 times sigma X into the formula that we had earlier. SNR is given by this equation, and XM is 4 times standard deviation. Then this is what we get. 6.02b minus 1.25 dB. What does this equation mean? It means that SNR increases 6 dB for every extra bit we put into quantization. For example, if we would like an SNR value of 90 dB, then the required B is around 16 bits. So for CD quality audio, 16-bit quantizers are used.